So just like when we were thinking about thermochemistry back in General Chemistry 1, we could think about the difference in, say, enthalpy between the reactants and products, which we called the delta H of the system. But we also talked about how each of those individual molecules in a reaction had its enthalpy, its own H, and it was the difference of all of those that gave us the delta. Similar analogies can be made with entropy, where each individual molecule has its own standard molar entropy, and we can use the difference of the standard molar entropies of individual molecules in an overall reaction to tell us what the change in entropy is. So standard molar entropy, standard is just referring to standard temperature pressure conditions, which we already know well is denoted by this degree symbol. And molar is for a molar of that substance, which is the same as the standard. And so these are experimentally determined values. You have to measure them. And we sort of arbitrarily are measuring them versus that hypothetical perfect crystalline state at 0K, that third law of thermodynamics saying that that thing is being measured against sort of this fictitious hypothetical. And then simply the difference then is really going to be whatever the molar entropy is for the products minus that of the reactants. That's our entropy change for the system. That can be positive or negative for a particular system. And it's important to note that these are molar entropies. So when you look up a value that's been experimentally determined for S naught here for a molecule, that's per mole of the substance. So if you have a balanced chemical reaction that has a coefficient that's not 1, so like 2 or 3 or 4, then you're multiplying that quantity by that same coefficient. So let's do this with an example, and this is one we talked about before, where we already sort of intuitively thought that this was going to be an increase in entropy because you're starting with one molecule and you're splitting it in half. And so we would expect there to be more states available to these two molecules than there were for this one. And so we can look at tables of these thermodynamic data and then look up what is the molar standard molar entropy of the product here, which would be NO2, and we can find that value, and we can do the same thing for N2O4, and then we can tabulate this. So I just grabbed these numbers straight from a table, which is in your textbook or any general chemistry textbook, and I just tabulated as we described. So it's just the sum of the products minus the sum of the reactants for those standard molar entropies. Being careful here to multiply by that coefficient. So we had 2 moles of NO2 being produced, so 2 moles times 240 joules per Kelvin mole. So entropy is typically measured in these units, joules per Kelvin mole, because it's a molar quantity. And then 1 mole for the N2O4 times the value from the table, 304.3, and that difference gives us a positive value for delta S, which is 175.7 joules per Kelvin. But remember, these are standard conditions. So these are all considering 1 molar conditions at 25 C and atmosphere of pressure. Either way, under those standard temperature pressure conditions, we can say that this system has an increase in entropy, which is a favorable condition for the universe, which contributes potentially to whether or not this will be spontaneous.